For most of modern science, the early universe was described as an empty place. Not empty in the absolute sense, but empty of structure, empty of complexity, empty of anything resembling order. In the first few 100 million years after the Big Bang, matter was thinly spread, light dominated over mass, and gravity had only just begun to assert itself. The universe was expanding faster than it could organize. This assumption sits quietly beneath almost everything we believe about cosmic history. It explains why stars appear when they do, why galaxies grow slowly, why complexity is delayed. And for decades, this picture worked. The earliest galaxies ever observed were small, irregular, and chaotic. They looked exactly like what the models predicted: fragile assemblies of stars, barely holding together under gravity's pull. Then, the observations changed. At first, the change was subtle enough to dismiss. A galaxy appeared slightly brighter than expected. Another looked slightly more massive. A spectrum showed chemical features that seemed premature. Each case could be explained away. Distance estimates are difficult. Dust alters light. Early measurements are noisy. But as observational technology advanced, the dismissals became harder to justify. The universe kept showing the same anomaly, again and again. When astronomers began using instruments capable of probing the earliest epochs of cosmic history with unprecedented clarity, they expected to see the universe's childhood. What they found instead looked disturbingly mature. Light arriving from extreme distances revealed galaxies that were not only present, but developed. Their stellar populations suggested multiple generations of star formation. Their mass implied efficient accumulation of matter. Their structure indicated stability. None of that should have been possible so early. To grasp why this is so unsettling, it helps to understand how galaxies are supposed to form. In the standard picture, dark matter collapses first. Invisible halos form the scaffolding of future galaxies. Ordinary matter follows, cooling slowly as it falls inward. Stars ignite one by one. Supernovae disrupt growth, regulating how fast matter can accumulate. It is a messy, inefficient process. Feedback slows everything down. That inefficiency is critical. Without it, galaxies would grow too fast, too large, too early. And yet, that is exactly what the universe appears to have done. Some of the galaxies now being observed existed less than 500 million years after the Big Bang. At that age, the universe was barely 10% of its current size. And yet, these galaxies already contained billions of stars. Some rival the Milky Way in mass. This creates a direct contradiction. According to current models, there simply has not been enough time. Stars must form. They must live. They must die. They must enrich their surroundings with heavier elements. Only then can later generations of stars and planets emerge. That cycle takes time, but the light tells us that the cycle was already well underway almost immediately. Astronomers examining the spectra of these early galaxies found signatures of elements heavier than hydrogen and helium, carbon, oxygen, nitrogen. These elements are not primordial, they are forged in stars. Their presence means that multiple stellar generations had already lived and died in the universe's earliest moments. Which raises an obvious question. Where did the time come from? At first, researchers attempted to solve the problem by adjusting parameters. Perhaps star formation was more efficient early on. Perhaps the first stars were unusually massive and short-lived. Perhaps feedback processes behaved differently in extreme conditions. These ideas help, but only partially. Even under optimistic assumptions, the gap remains. The universe appears to have moved faster than it should have been able to, and this speed is not limited to a single object. It appears across populations. Entire catalogs of early galaxies show the same issue. Too big, too massive, too evolved, which suggests that the anomaly is not local. It is systemic. This is the point where cosmology becomes uncomfortable, because systemic problems cannot be dismissed as measurement errors. They demand explanation, and explanations so far are incomplete. Some scientists have suggested that our distance measurements might be wrong. that these galaxies are not as old as they appear, that gravitational lensing or unusual light distributions are misleading us. These possibilities are investigated carefully, but as independent measurements converge, the uncertainty shrinks, the distances hold, the ages remain, the problem persists. What makes this particularly troubling is that cosmology is not an imprecise science. The early universe is constrained by the cosmic microwave background, radiation left over from when the universe was only 380,000 years old. That radiation carries detailed information about the initial conditions of cosmic structure. Those conditions should limit how fast galaxies can form, and yet the galaxies we observe appear to violate those limits. This creates tension between different parts of our understanding. The early universe, as revealed by the cosmic microwave background, suggests a slow start. The early universe, as revealed by galaxies, suggests a rapid buildup. Both cannot be fully correct under the same assumptions. Something has to give. At this stage, scientists are careful with their language. They use words like unexpected and surprising. They speak of tension rather than contradiction. But behind the caution lies unease, because this is not a small discrepancy. It goes to the heart of how structure forms. If galaxies can form this quickly, then gravity behaved differently in the early universe, or matter did, or both. And that possibility opens doors that physics is not yet ready to walk through. Because once you allow the early universe to behave differently, you are forced to reconsider everything that follows. The timeline of star formation, the emergence of black holes, the growth of cosmic structure on the largest scales. The early universe may not have been a slow, hesitant place. It may have been aggressive, efficient, productive, and that realization carries consequences far beyond astronomy. Because if complexity arises quickly once conditions allow, then the universe does not waste time, it builds. Which leads to a deeper, quieter question. If galaxies could form so rapidly, what else could have emerged earlier than we assumed? This question lingers uncomfortably at the edges of modern cosmology. It is not asked loudly, but it is there, because time has always been the universe's greatest constraint. Remove or loosen that constraint, and the entire story changes. The early universe stops being a prologue. It becomes an active chapter. And the observation that triggered this shift is deceptively simple. We are seeing structures that should not exist, not because they are impossible in principle, but because they are impossible on the timeline we thought governed reality. And timelines in physics are not optional. They are consequences of laws, which means that either the laws behave differently or our understanding of them is incomplete. This is the observation. Everything else follows from it. The more carefully scientists examine these early galaxies, the more difficult it becomes to explain them away. In astronomy, brightness is not just a visual property, it is a clue. Brightness tells us how many stars exist, how massive they are, and how efficiently matter has been converted into structure. When astronomers measure the brightness of these early galaxies, they are not guessing. They are translating photons into physical quantities, and those quantities do not make sense. Some of these galaxies emit light equivalent to billions of suns. Others display rotational behavior that implies deep gravitational wells. In several cases, the inferred mass exceeds what simulations predict should be possible by factors that cannot be ignored. The universe appears to have assembled matter with extraordinary speed. This speed becomes even more unsettling when black holes enter the picture. At the centers of many galaxies sit supermassive black holes. In the modern universe, these objects contain millions or billions of times the mass of the Sun. They are thought to grow slowly, feeding on surrounding gas and stars over immense spans of time. But in the early universe, astronomers are finding black holes that are already enormous. Some existed less than 1 billion years after the Big Bang. Their mass presents a severe problem. Black holes cannot grow arbitrarily fast. Even under ideal conditions, there are physical limits on how quickly matter can fall inward. Radiation pressure resists collapse. Accretion disks regulate growth. And yet, these early black holes appear fully grown. They should not have had time to reach such size. This deepens the contradiction. Galaxies appear too large. Black holes appear too massive. Chemical complexity appears too advanced. All too early. Each of these anomalies alone would be troubling. Together, they form a pattern suggesting that the early universe was not merely active, but extraordinarily efficient at creating structure. This efficiency challenges one of the quiet assumptions in cosmology, that feedback mechanisms prevent runaway growth. In the modern universe, star formation is self-limiting. As stars form, they heat surrounding gas, drive winds, and suppress further collapse. This keeps galaxies from consuming all available material too quickly. But the early universe may not have followed the same rules. Conditions were different. Densities were higher. Background radiation was stronger. It is possible that feedback was less effective, allowing matter to collapse rapidly. But even this explanation has limits. Feedback alone cannot account for the observed scale of early structures. The math still resists, which leads to a more uncomfortable possibility. The laws governing structure formation may not have been constant across cosmic time. Physics assumes that the fundamental rules of nature do not change. Constants remain constant. Forces behave consistently. This assumption underpins everything from particle physics to cosmology. But what if that assumption is only approximately true? The early universe was extreme, beyond anything we can recreate. Temperatures were higher, energies were immense, conditions were unfamiliar. It is possible that gravity behaved differently, that matter interacted in unexpected ways, that processes we do not yet understand dominated structure formation. This idea is unsettling because it pushes physics into uncertain territory. It suggests that our current models, successful though they are, may be incomplete descriptions of reality, and incompleteness at the foundation has consequences. Because once you admit that the early universe followed different rules, you are forced to ask where else those differences mattered. Did they affect how matter clustered? Did they influence how quickly stars ignited? Did they change the pace at which complexity emerged? These questions do not have comfortable answers, which is why they are often approached cautiously. But the observations refuse to disappear. They are persistent, they accumulate, and they intersect with other tensions in cosmology. Measurements of the universe's expansion rate disagree depending on how they are taken. Early universe measurements and late universe measurements produce incompatible results. This is known as the Hubble tension. It is not a small discrepancy. It has survived years of scrutiny, and it points, once again, to the early universe. Something about the initial conditions may be misunderstood. Something about how energy, matter, and expansion interacted may not fit neatly into our current framework. When scientists encounter multiple tensions pointing to the same epoch, they pay attention, because that is often where new physics hides. The early universe is becoming such an epoch, and the galaxies that should not exist are its most visible symptom. They are not subtle anomalies buried in equations. They are bright, observable, direct. They force confrontation, which brings us to an important realization. The universe does not care about our expectations. It reveals itself through observation, not comfort. And when observation contradicts theory, it is theory that must adapt. Historically, these moments mark transitions. They do not arrive with certainty. They arrive with confusion, with arguments, with debate, with scientists insisting that the problem will resolve itself. Sometimes it does. Sometimes it does not. The early galaxies may belong to the second category because they force a reconsideration of time itself. Time in cosmology is not just a coordinate, it is a resource. It limits what can happen. But what if the early universe effectively compressed time? Not literally, but functionally. If processes occurred faster, if efficiencies were higher, if collapse was more aggressive, then the universe could achieve in hundreds of millions of years what we assumed required billion. This idea is deeply unsettling. because it suggests that complexity may be a natural outcome of cosmic conditions, not a rare accident. It implies that once matter crosses certain thresholds, organization accelerates. And that acceleration may have occurred far earlier than we thought. This reframes the early universe. Instead of a slow, hesitant beginning, it becomes a period of rapid construction. Stars ignite quickly. Galaxies assemble aggressively. Black holes grow voraciously. The universe builds. And if that is true, then the observation that triggered this discussion is not merely a curiosity, it is a clue. A clue that the universe is more capable than we assumed, more efficient, more willing to organize itself, which raises a subtle but profound implication. If complexity emerges quickly, then the window for cosmic evolution expands. Events we believed belonged to the distant future may have occurred near the beginning. The universe may have matured far sooner than we imagine, and that forces a reconsideration of what early really means. In cosmology, early usually implies primitive, but these galaxies are anything but primitive. They are sophisticated systems, and sophistication requires history, which brings us back to the central tension. Where did that history come from? If the timeline is correct, then the universe somehow condensed an enormous amount of development into a remarkably short span. If the timeline is wrong, then our measurements of cosmic distance and age are flawed. Either way, the implications are serious, because the universe does not leave much room for error. Its history is written in light, and that light is telling us something uncomfortable. It is telling us that parts of the universe existed in states they should not have reached so quickly. That structure did not wait, that complexity did not hesitate, and that the story we tell about cosmic evolution may be missing a critical chapter. This is no longer a question of whether something unusual has been observed. That question has already been answered. The question now is why. And answering that will require confronting assumptions we have carried quietly for decades. Assumptions about time, about efficiency, about how reality builds itself from nothing. The observation forces us to look closer, and the closer we look, the more difficult it becomes to maintain the idea that the early universe was simple. It may have been anything but. As these observations accumulated, a quiet shift began to take place in cosmology. Not a public one, not a dramatic announcement, but a subtle change in how scientists spoke when they thought no one was listening. In private discussions, in conference halls, in the careful language of research papers, a new phrase appeared more often than expected. Model strain. It is a polite term, a restrained term, but what it means is simple. The universe is no longer behaving the way our models expect it to. In science, models are not decorative. They are predictive machines. When they fail repeatedly under independent observations, something fundamental is wrong, and the failure here is not marginal. It concerns the speed at which order emerges. To understand the depth of this problem, consider how tightly constrained the early universe is. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. That snapshot is extraordinarily precise. It tells us how matter was distributed, how dense regions were, and how fluctuations behaved. From that snapshot, cosmologists evolved the universe forward using known physics. This is not guesswork, it is computation. And when they do this, the resulting universe does not resemble what we are now observing. The simulated universe grows too slowly. Structures lag behind reality. Galaxies take longer to form. Black holes remain smaller. Chemical enrichment progresses at a measured pace. Reality, by contrast, appears impatient. This discrepancy forces scientists to confront an uncomfortable possibility. The early universe may not have evolved smoothly. Instead of a gradual progression, it may have undergone rapid transitions, phases where structure formation accelerated dramatically. In physics, such transitions are not unheard of. Water freezes suddenly, materials change phase, symmetry breaks. The early universe itself is thought to have undergone multiple phase transitions as it cooled. If one of those transitions altered how matter behaved, how efficiently it collapsed, cooled, or clustered, it could explain the rapid emergence of structure. But identifying such a transition is not simple. It would require new physics, and new physics is not introduced lightly. Because once you open that door, it does not close easily, yet the data keeps pressing. Beyond galaxies and black holes, there are other signs that the early universe may have behaved differently. Large-scale surveys reveal unexpected alignments in galaxy distributions, patterns that appear too coherent, too organized, given the randomness expected from inflation. Some researchers argue these are statistical flukes. Others are not so sure. The universe, on its largest scales, may carry memory of conditions we do not yet understand. If that is true, then the early universe was not just a starting point. It was an active architect. This idea challenges a deep assumption that complexity is always downstream, that it flows forward slowly, accumulating only after long delays. But what if complexity can appear abruptly once thresholds are crossed? What if the universe, once cooled just enough, rapidly organized itself into structures that resemble maturity? In that case, the galaxies we observe are not anomalies, they are consequences. And that possibility forces us to reconsider the meaning of early. In everyday thinking, early implies unfinished. But in physics, early may simply mean extreme. Extreme conditions can produce extreme outcomes. The early universe was not quiet. It was energetic, dense, dynamic. Under such conditions, matter may have behaved in ways we have never observed since. This creates a gap in our understanding. Modern physics is built on experiments conducted under present-day conditions. We extrapolate backward, assuming the rules remain unchanged. But extrapolation is only reliable within limits. The early universe may lie beyond them, which brings us to a subtle but critical realization. Our confidence in cosmic timelines depends on assuming continuity, that what we observe now is a slowed-down version of what happened then. But if the early universe operated under different regimes, that assumption breaks. And when continuity breaks, history compresses. The universe's story becomes less linear, less predictable. This possibility unsettles cosmologists, not because it is exotic, but because it undermines certainty. It suggests that the universe's earliest chapter may not be fully recoverable from present-day physics alone. We may be missing rules that only applied briefly and left behind only indirect traces. The galaxies that should not exist may be such traces. They may be fossils of a period when structure formation was turbocharged. And if that is true, then the early universe was not a blank slate. It was primed, ready to build, which leads to another troubling implication. If the universe can organize itself quickly, then complexity is not rare. It may be inevitable. Given the right conditions, matter may naturally assemble into sophisticated systems far faster than we assumed. This idea extends beyond galaxies. It touches the emergence of stars, planets, chemistry, and potentially environments capable of supporting complexity at other levels. The early universe may have been fertile sooner than expected, and that changes how we think about cosmic history. Because our story of the universe often includes a long delay, a waiting period before anything interesting happens. But what if that delay was an illusion? What if the universe moved from simplicity to complexity in a rush? If so, then the galaxies we observe are not exceptions. They are evidence that the universe's capacity for organization is far greater than our models allow. And this realization creates a quiet tension with another foundational idea, the idea that the universe is indifferent, that it does not favor complexity, that structure emerges reluctantly against entropy's pull. But the early galaxies suggest the opposite. They suggest eagerness. They suggest that once conditions permit, the universe wastes no time. It builds. This does not mean purpose. It does not imply intention, but it does imply efficiency. And efficiency at cosmic scales is unsettling, because it forces us to confront the possibility that complexity is not fragile. It may be robust, resilient, hard to suppress. And if that is true, then the early universe may have crossed thresholds that we do not yet understand. Thresholds that allowed matter to self-organize rapidly and extensively. The galaxies that should not exist may mark where those thresholds were crossed. They are not errors. They are signals. Signals that the early universe operated in a regime that current physics only approximates. And that regime may hold answers to questions we have not yet fully articulated. Questions about how matter behaves under extreme conditions. Questions about how structure emerges. Questions about whether our assumptions about time, causality, and gradualism truly apply at the beginning of everything. The discomfort comes from recognizing that we are not just missing details. We may be missing mechanisms, and mechanisms, once discovered, often change everything. The early universe is no longer just a backdrop. It is becoming an active participant in its own organization. And the observation that triggered this shift, the existence of mature galaxies far too early, remains stubborn. It refuses to disappear. It resists explanation. And it continues to force cosmologists into deeper waters. Because once you accept that the universe built complexity faster than expected, you must ask the next question. If the early universe could do this, what else might it have done? Once the idea is allowed to settle, that the early universe may have organized itself far more efficiently than expected, it becomes difficult to contain its implications. Because efficiency changes everything. In physics, limits exist for a reason. They protect causality. They preserve order. They ensure that processes unfold in predictable ways. When those limits appear to be exceeded, even slightly, it is rarely an isolated event. It suggests that the boundary itself is misunderstood. The early universe now sits uncomfortably close to such a boundary. The galaxies that should not exist are not singular curiosities. They are markers, signposts pointing toward a deeper inconsistency between expectation and reality. And that inconsistency forces a reconsideration of how we think about beginnings. We tend to imagine the universe starting slowly, like an engine idling before acceleration, a gentle ramp from simplicity toward complexity. But what if the universe did not idle? What if it accelerated immediately? In that case, the earliest moments after the Big Bang were not merely preparatory, they were decisive. Conditions may have aligned in such a way that structure formation was not just possible, but inevitable and fast. This would mean that the universe crossed critical thresholds almost immediately, thresholds beyond which matter no longer behaved passively, beyond which gravity did not merely pull, it organized, beyond which complexity was no longer delayed. Such thresholds are familiar in other domains of physics. At certain temperatures, materials change state. At certain pressures, new phases emerge. At certain energies, symmetries break. The early universe passed through many such conditions. It is not unreasonable to suspect that one of them altered how structure formed. And if so, the effects would ripple outward across cosmic history. The first stars would ignite sooner. The first galaxies would assemble rapidly. The first black holes would grow aggressively. The universe would mature early. And maturity has consequences. A mature universe behaves differently from a young one. It has structure, gradients, hierarchies. It can channel matter more efficiently. It can amplify small differences into large-scale organization, which means that once maturity is reached, further complexity becomes easier, not harder. This creates a feedback loop. Early efficiency begets later efficiency, and this may explain why the universe today appears so richly structured, because it did not crawl toward complexity, it sprinted. This idea challenges another quiet assumption, that the universe resists organization. Entropy is often invoked as an explanation for disorder, but entropy does not forbid structure. It only constrains how structure must be paid for. And the early universe was rich in energy. It had resources. It could afford to build. If that energy was channeled efficiently, if matter collapsed rapidly and coherently, then complexity would not be delayed. It would emerge naturally. This reframing alters the emotional tone of cosmology. The universe becomes less fragile, less hesitant, more capable. And capability implies potential, which leads to a subtle but profound shift in perspective. We often think of the universe as a place where complexity is rare, fragile, and easily destroyed. But the early galaxies suggest the opposite. They suggest that complexity emerges readily when conditions allow, that once the rules permit, structure follows quickly, and that has implications far beyond galaxies. It touches the formation of stars, planets, chemistry, and environments capable of sustaining long-lived processes. The early universe may not have been barren for long. It may have been fertile almost immediately. This does not mean that everything followed smoothly. It does not mean that complexity was stable, but it does mean that the universe was capable of organizing itself earlier than we assumed, which forces us to ask a question that cosmology has traditionally avoided. If the universe matured quickly, what else might have emerged earlier than expected? This question is not asked lightly, because it pushes beyond observation into inference, and inference, when untethered, can drift. But the data invites the question. It does not answer it. It simply opens the door. The galaxies that should not exist force us to confront the possibility that our timeline is compressed, that cosmic history unfolded faster, that what we thought required patience may have required only conditions. And this realization destabilizes comfort, because if time is not the bottleneck we believed it to be, then many assumptions about rarity must be revisited. We assumed certain events were unlikely because they required long durations. But if those durations were shorter, then the universe may be more active than we imagined. This does not imply intention. It does not imply design. But it does imply that the universe is efficient at exploring its own possibilities. And that efficiency makes anomalies less exceptional. It makes rapid emergence plausible. The early galaxies in this view are not errors. They are outcomes. Outcomes of a universe that wasted no time. And this is why the observation is so difficult to dismiss, because it does not rely on speculative physics. It relies on light, on photons that have traveled across nearly the entire age of the universe to reach us. They carry information about structure, composition, and history. They do not speculate. They report, and their report is clear. Structure appeared early. Complexity arrived quickly. The universe did not wait. This does not mean that our models are wrong in every respect, but it does mean that they may be incomplete at the foundation. And incompleteness at the foundation propagates upward. It affects how we interpret everything that follows, which is why the galaxies that should not exist represent more than a puzzle. They represent a pressure point, a place where assumptions meet reality, a place where the universe reminds us that our stories are provisional, that our confidence is conditional, that observation always has the final word. And this is where section 1 ends, with an observation that refuses to be ignored, with evidence that resists easy explanation, with a universe that appears to have moved faster than we allowed it to. In the sections ahead, we will examine why this observation creates such deep conflict with modern cosmology. We will explore the limits of existing explanations, and we will confront what it would mean if the universe's earliest chapter was not slow, but decisive. Because once you accept that this part of the universe should not exist, the rest of the story becomes impossible to ignore. If the observation alone were the only problem, cosmology might absorb it. An anomaly can be tolerated, a surprise can be investigated, a discrepancy can be refined away. But the real difficulty begins when the observation is placed inside the framework that is supposed to explain it. Because that framework was never designed to accommodate this outcome, modern cosmology rests on a carefully balanced structure of assumptions, equations, and constraints. Each part reinforces the others. Remove one, and the entire system shifts. The existence of massive, mature galaxies in the early universe applies pressure precisely where that balance is most delicate. At the foundation lies the standard cosmological model. It describes a universe dominated not by visible matter, but by invisible components, dark matter and dark energy. These unseen ingredients shape the expansion of space and the growth of structure. Dark matter provides the gravitational scaffolding. Dark energy drives accelerated expansion. Ordinary matter follows their lead. Together, they form a framework that has explained decades of observations with remarkable success. But that success depends on timing. Structure must grow slowly enough to remain consistent with early universe conditions, yet fast enough to produce the universe we see today. This balance is fragile, and the early galaxies push directly against it. In simulations based on the Standard Model, dark matter halos formed first. They merge gradually, growing larger over time. Gas falls into these halos, cools, and forms stars. The process is hierarchical and incremental. There is no mechanism for skipping steps. And yet, the universe appears to have skipped several. The early galaxies imply that dark matter halos became massive very quickly, that gas cooled efficiently, that star formation surged rather than ramped. Each of these implications stresses a different part of the model. Taken together, they suggest that the model's assumptions may be incomplete. One of the first points of strain appears in how dark matter behaves. Dark matter is assumed to be cold and slow-moving. This allows it to clump effectively, forming the backbone of galaxies. But even cold dark matter has limits. Its collapse rate is constrained by initial conditions encoded in the cosmic microwave background. Those conditions do not permit the rapid formation of extremely massive halos so early, yet the galaxies suggest otherwise. This forces cosmologists into an uncomfortable corner. Either dark matter behaved differently in the early universe, or our interpretation of its role is flawed. Some have proposed alternative forms of dark matter, particles that interact differently, that collapse more quickly, that alter structure formation on small scales. But each modification carries consequences. Change dark matter too much, and you disrupt the agreement with large-scale structure. Change it too little, and the early galaxies remain unexplained. The window for adjustment is narrow, and that is only one part of the problem. Another strain appears in star formation itself. Star formation is regulated by feedback. As stars form, they inject energy into their surroundings. Radiation heats gas. Supernovae drive outflows. Growth slows. This feedback is essential. Without it, galaxies would consume their gas rapidly and burn out. But early galaxies appear to have formed stars at extraordinary rates. Either feedback was weaker, or something suppressed its effects. Both possibilities challenge assumptions built into simulations. Weak feedback allows rapid growth, but leads to overproduction of stars later. Strong feedback preserves later behavior, but prevents early growth. The model struggles to satisfy both. And then there is the issue of black holes. Supermassive black holes require time. Even starting from large initial seeds, their growth is limited by physical processes that regulate accretion. Yet the early universe contains black holes that are already enormous. Explaining them requires either exotic formation pathways or sustained periods of extreme growth. Both options strain credibility because they must occur frequently, not rarely. This is not about one exceptional object. It is about a population, which means the explanation must be general. The Standard Model was not built for this. It was built to explain gradualism. And gradualism is precisely what the early universe appears to defy. This creates a deeper conceptual conflict. The model assumes that complexity emerges reluctantly, that it must fight against expansion, entropy, and feedback. But the observations suggest the opposite. They suggest that complexity emerges eagerly. Once conditions permit, structure explodes into existence. This is not just a technical issue, it is a philosophical one, because it forces us to reconsider the nature of cosmic evolution. Is the universe conservative in its behavior or opportunistic? Does it resist organization, or does it pursue it whenever possible? The Standard Model implicitly assumes resistance. The early galaxies imply opportunism. Reconciling these views is not easy. It may require rethinking how we interpret early universe constraints. It may require new physics. Or it may require abandoning assumptions that have quietly guided cosmology for decades. None of these options are comfortable, which is why the problem has not been solved. Instead, it has been managed. Researchers adjust parameters. They refine simulations. They add complexity. But each fix introduces new tensions elsewhere. The model becomes more elaborate, less elegant. And elegance, in physics, is not aesthetic. It is diagnostic. When a theory requires excessive tuning, it often signals that something deeper is missing. The early universe may be exposing such a gap because the model works exceptionally well at some scales and struggles profoundly at others. This mismatch is not random. It points toward the moment when structure first emerged, which suggests that the earliest chapter of cosmic history may be the least understood, not because it is inaccessible, but because we have underestimated it. The early universe may have been more dynamic, more aggressive, and more capable than our models allow, and the galaxies that should not exist are forcing that realization into the open. They are not asking for minor revisions. They are asking for reconsideration of assumptions, of timeline, of how the universe builds itself. This is where Section 2 truly begins, because the problem is no longer observational, it is theoretical, and theory, once trained, does not recover easily. As attempts to resolve the problem multiplied, an unexpected pattern emerged. Each proposed solution fixed one tension, only to amplify another. This is a warning sign in physics. When a theory requires increasingly precise adjustments to remain viable, it begins to lose explanatory power. It stops predicting and starts accommodating. The early universe galaxy problem has pushed cosmology dangerously close to that line. Consider the most common strategy: increasing the efficiency of star formation. If stars formed faster in the early universe, galaxies could grow large more quickly. On paper, this sounds reasonable. Early gas clouds were denser. Cooling mechanisms may have been different. The first stars may have been unusually massive, but increasing star formation efficiency has consequences. Stars do not form quietly. They radiate, they explode, they inject energy into their surroundings. If early star formation were too efficient, feedback would become overwhelming. Gas would be heated and expelled. Future star formation would be suppressed. The result would be galaxies that burn brightly and then fade prematurely. That is not what we observe. Many early galaxies appear sustained, not self-destructive, which suggests that feedback was somehow muted. But muting feedback creates a different problem. Without feedback, galaxies later in cosmic history would become too massive, too quickly. The present-day universe would not resemble what we see. Fixing the early universe breaks the late universe. This pattern repeats. Another proposed solution involves changing how dark matter behaves. If dark matter clumped more efficiently early on, massive halos could form sooner. Gas would fall in rapidly. Galaxies would assemble faster. But dark matter behavior is constrained by multiple independent observations. Change it too much, and you disrupt the cosmic microwave background. You alter large-scale structure. You break agreement with galaxy clustering at later times. The freedom to modify dark matter is limited. And yet, the early galaxies seem to demand modification. This creates a narrowing corridor of possibility. Inside it, models must be tuned with increasing precision. Outside it, they fail outright. Such corridors are uncomfortable places for theory to live. They suggest that the underlying picture may be missing a piece. Another approach invokes exotic black hole formation pathways. Perhaps supermassive black holes form directly from collapsing gas clouds, bypassing the slow growth phase. This could explain their early appearance. But this explanation introduces its own difficulties. Direct collapse black holes require very specific conditions: low metallicity, suppressed star formation, intense radiation backgrounds. Those conditions are rare, yet early massive black holes are not. They appear too frequently to be explained by exceptional circumstances. Once again, the explanation must be general, and general explanations are harder to find. Some researchers propose that our interpretation of observations is flawed. Perhaps the masses of these galaxies are overestimated. Perhaps their light is misleading. This possibility is taken seriously. Astronomers scrutinize their assumptions. They test alternative models of stellar populations. They reanalyze data. But even conservative estimates leave a gap. The galaxies are still too massive. The problem shrinks, but it does not disappear, which leads to a deeper realization. This is not a problem of measurement alone. It is a problem of expectation. Our models expect the universe to behave in a certain way. The universe does not comply. This mismatch forces cosmology into a defensive posture. Instead of predicting what should exist, models are increasingly asked to explain what already does. That reversal is subtle but significant. Prediction is the hallmark of understanding. Accommodation is the hallmark of uncertainty. And the early universe galaxy problem is pushing cosmology toward the latter. This is why the tension has persisted. It is not because scientists are careless. It is because the problem resists simple solutions. Every path forward leads through trade-offs. Solve one issue and another appears. This cascading failure suggests that the problem may not lie in the details. It may lie in the framework itself. The standard cosmological model assumes smoothness. It assumes that processes average out over time. But the early universe may have been punctuated by rapid, non-linear events, bursts of activity, threshold crossings, runaway collapses. Such behavior is difficult to capture in models designed for gradualism. It requires a different mindset. Instead of assuming slow evolution, one must consider rapid transitions. Instead of incremental growth, one must consider leaps. This is uncomfortable territory, because leaps are harder to control. They defy intuition. They resist simple explanation. Yet nature often operates this way. Phase transitions are abrupt. Critical phenomena are non-linear. Small changes can have outsized effects. The early universe may have been dominated by such behavior. If so, then our models, built on smooth extrapolation, are poorly suited to describe it. This would explain why adjustments fail. They are applied within a framework that is not designed to handle rapid change. And so the universe keeps slipping through the cracks. This realization does not imply that the standard model is wrong in every respect. It works remarkably well across vast scales, but it may be incomplete where conditions were most extreme. And incompleteness at the beginning propagates forward because the early universe sets the stage. Its behavior determines initial conditions for everything that follows. If those conditions are misunderstood, then later agreement may be coincidental rather than fundamental. This is why the early galaxies matter so much. They are not just anomalies. They are leverage points. They apply force where theory is weakest, and they reveal where our confidence is least justified. The longer the tension persists, the harder it becomes to ignore. At some point, the cost of maintaining the existing framework exceeds the cost of revising it. Cosmology may be approaching that point, not because of one observation, but because of many, all pointing toward the same conclusion. The early universe was not as simple as we thought, and simplicity was never guaranteed. Once gradualism begins to fracture, the consequences extend far beyond any single anomaly. Gradualism is not just a modeling choice. It is a worldview embedded in modern cosmology. It assumes that change is slow, cumulative, and predictable, that large outcomes require long durations, that complexity must earn its existence through time. The early universe appears to contradict this assumption, and when a foundational assumption fails, its failure propagates. If structure did not grow slowly, then the universe's history is not a smooth curve. It is a series of inflection points, moments when conditions crossed thresholds, moments when behavior changed abruptly, moments when the universe reorganized itself. This possibility forces cosmology into unfamiliar territory because it suggests that cosmic history may be dominated not by steady evolution, but by transition. And transitions are dangerous to predict. They are sensitive. They are non-linear. They amplify small differences into large outcomes. In such systems, initial conditions matter enormously. And that brings us back to the earliest moments of the universe. The initial fluctuations encoded in the cosmic microwave background are small, barely 1 part in 100,000. In a gradual universe, such fluctuations grow slowly. In a transition-driven universe, they may grow explosively. If the early universe crossed a threshold that enhanced gravitational collapse, those tiny fluctuations could have become massive structures very quickly. This would explain why galaxies appear early and mature. But it would also imply that the early universe was unstable in ways our models do not capture. Instability in physics is not chaos. It is sensitivity. And sensitive systems behave very differently from stable ones. They evolve quickly. They reorganize. They settle into new regimes. The early universe may have done exactly that. If so, then the period we think of as early may have been extraordinarily eventful, not a quiet beginning, but a turbulent one. This reframing alters how we interpret cosmological evidence. The absence of gradual buildup is no longer puzzling. It is expected. The presence of early complexity is no longer anomalous. It is natural. Under this view, the early universe did not wait to become interesting. It became interesting immediately, which raises a difficult question. If the universe underwent rapid transitions early on, why do we not see direct evidence of them today? The answer may lie in how information survives. The universe expands. Structures merge, signals dilute. Early events leave faint imprints. Most of what happened at the beginning has been erased or smoothed over by billions of years of evolution. Only indirect clues remain. The early galaxies may be among those clues. They are relics of a time when structure formation was accelerated. They survived because they were large enough, massive enough, and stable enough to persist. Smaller structures may have been destroyed, merged, or absorbed, which means we are seeing a biased sample, the universe's survivors. This introduces a subtle but important distortion. Our observations are dominated by what endured, not by what existed. And endurance favors scale. Large structures survive, small ones vanish. This bias may exaggerate the appearance of rapid complexity, but it does not eliminate it. Even accounting for survival bias, the scale of early galaxies remains difficult to explain, which suggests that something genuinely unusual occurred. If gradualism fails, then cosmology must confront the possibility that the universe is not governed by a single mode of behavior. It may switch modes. Under certain conditions, it may favor rapid organization. Under others, slow evolution. The early universe may have occupied a regime we no longer experience, and that regime may have allowed matter to self-organize with unprecedented speed. This is not a comforting idea, because it implies that our current physical intuitions are limited. They are shaped by the universe as it is now, not as it was then. Extrapolating backward assumes continuity. Transitions violate continuity. They create breaks, and breaks create blind spots. The early universe may reside in one such blind spot. This would explain why efforts to fix the problem within existing models keep failing. They are trying to describe a regime using tools designed for a different one. This is like modeling turbulence with equations meant for laminar flow. The math works until it doesn't, and when it doesn't, small discrepancies become large ones. The early galaxies may be the visible manifestation of such a mismatch. They are where the equations stop agreeing with reality, and that disagreement is not subtle. It is structural, which leads to a deeper implication. If the early universe experienced rapid transitions, then cosmic history is not monotonic. It is punctuated. There may have been bursts of structure formation, bursts of black hole growth, bursts of complexity. Between them, quieter periods. This rhythm would reshape how we think about cosmic time. Instead of a steady progression, it becomes episodic, and episodic systems are harder to predict. They do not average out. They remember their past in complicated ways, which brings us back to memory. If the universe experienced early transitions, their effects may persist subtly, in alignments, in distributions, in anomalies we have not yet fully interpreted. The early universe may have left fingerprints that we are only beginning to recognize. The galaxies that should not exist may be the clearest of those fingerprints. They announce, without drama, that something about the early universe is different. Not wrong, different. And difference is more unsettling than error, because error can be corrected. Difference requires understanding. This realization places cosmology at a crossroads. Either the anomalies will resolve as data improves, or they will force a revision of how we think about cosmic evolution. History suggests that persistent anomalies rarely disappear quietly. They either fade quickly or they transform theory. The early galaxies have not faded, they have multiplied, and that persistence makes the second outcome increasingly likely. Which brings us to the edge of the framework. If gradualism fails, if transitions dominate, if efficiency replaces patience, then the universe's earliest chapter may be fundamentally unlike anything that followed. And that chapter may hold answers to questions we have not yet learned how to ask. Questions about how structure emerges. Questions about how matter behaves under extreme conditions. Questions about whether our current physics is a special case rather than a universal description. The early universe may not have been governed by the same rules we observe today. And the galaxies that should not exist may be the universe's way of reminding us of that. At some point, a framework stops being flexible and starts becoming fragile. Not because it is wrong, but because it has been stretched beyond the conditions it was built to describe. Cosmology may be approaching that point. The early universe observations do not demand that we discard everything we know, but they do demand that we confront the possibility that our framework is incomplete in precisely the place where it matters most. At the beginning, frameworks shape interpretation. They decide which questions are asked, which answers are considered plausible, and which anomalies are tolerated as noise. When a framework works well, it fades into the background. It becomes invisible. When it struggles, it becomes impossible to ignore. The early galaxies have made the framework visible again. They have forced cosmologists to look not at data, but at assumptions. Assumptions about time, about efficiency, about how matter organizes itself under extreme conditions. Revising those assumptions is not a technical task. It is a conceptual one, because the standard cosmological model is not just a set of equations. It is a narrative. It tells a story of a universe that begins simple, grows slowly, and only later achieves complexity. That story is elegant. It is also comfortable. But elegance is not evidence, and comfort is not truth. If the universe tells a different story, it is our responsibility to listen. Revising the framework does not mean abandoning rigor. It means expanding it. It means allowing for the possibility that the universe operates in regimes we do not yet understand. That the early universe was governed by dynamics that no longer dominate. That the laws we observe today are not the whole story, but a late-time approximation. This idea is not unprecedented. Physics has encountered it before. Classical mechanics works until it doesn't. Thermodynamics holds until extremes intervene. Relativity emerges where Newton fails. Each transition did not invalidate what came before. It contextualized it. The early universe may require a similar contextualization. Our current models may describe the universe after it settled, not while it was still finding its structure. If that is the case, then the early universe was not merely an earlier version of the present. It was a different environment altogether. And environments matter. They shape behavior. They determine which processes dominate. Under extreme conditions, new phenomena emerge. The early universe was nothing if not extreme. It is therefore reasonable, perhaps inevitable, that it behaved differently. The discomfort arises not from this possibility, but from its implications. If the early universe operated under different rules, then our reconstruction of cosmic history is provisional. We may be missing chapters. We may be misinterpreting transitions as gradual trends. We may be smoothing over events that were abrupt. This does not mean we know nothing. It means we know enough to realize that our picture is incomplete. And incompleteness at the foundation changes how we interpret everything built upon it. Which brings us back to the galaxies that should not exist. They are not asking us to speculate wildly. They are asking us to acknowledge limitation, to admit that our models do not fully capture reality at the beginning. That admission is not failure. It is progress, because physics advances not by defending frameworks, but by refining them, by recognizing where they fail, by letting observation guide revision. The early galaxies are guiding us, not loudly, not dramatically, but persistently. They appear again and again, each one reinforcing the same message. The universe matured faster than we thought, and that fact cannot be ignored indefinitely. Eventually, cosmology will have to choose. Either it will find a way to reconcile these observations within the existing framework, or it will expand the framework itself. Both paths are difficult. Both require humility, but only one aligns with history. When reality resists explanation, reality does not yield, theory does. And so Section 2 ends not with an answer, but with a recognition. The problem is not that the universe has violated our expectations. The problem is that our expectations may have been too narrow. The early universe may not fit comfortably inside the story we told ourselves. And that realization sets the stage for what comes next. Because once you accept that the framework may be incomplete, the question is no longer whether something is missing. The question becomes what. And discovering that will require looking beyond familiar explanations, beyond gradualism, beyond comfort, into the deeper structure of reality itself. Once the possibility of an incomplete framework is acknowledged, attention inevitably shifts toward explanation. Not explanation as resolution, but as exploration. Because when a problem resists a single answer, the only honest response is to consider multiple ones, each incomplete, each revealing something about the limits of what we know. The early universe anomaly has inspired exactly this kind of response. A growing landscape of ideas has emerged, each attempting to explain how massive, mature structures could appear so early. None are fully satisfying, but each illuminates a different corner of the problem. One of the most conservative explanations begins with the simplest assumption. Perhaps the early universe was not exotic at all. Perhaps it was merely faster. In this view, the laws of physics remain unchanged. What differs is efficiency. Star formation may have been far more effective in primordial environments. Gas clouds were denser, cooling pathways more direct. The first stars may have formed in bursts rather than trickles. This idea preserves continuity. It allows cosmology to remain intact while adjusting the pace of events. But pace is not free. Accelerating star formation requires suppressing feedback. It requires that energy injected by young stars fail to halt collapse. This is difficult to justify. Feedback is not optional. It emerges naturally from radiation and explosions. Suppressing it without introducing new physics is challenging. And even when feedback is minimized in simulations, the resulting galaxies still struggle to match observation. The explanation helps, but it does not solve. Another proposal shifts focus from stars to dark matter. Perhaps dark matter behaved differently under early universe conditions. Perhaps it was not perfectly cold or not entirely collisionless. If dark matter collapsed more aggressively, massive halos could form sooner. Gas would follow. Structure would accelerate. This idea is attractive because dark matter already lies beyond direct observation. Modifying its properties feels permissible, but dark matter is constrained indirectly by many observations. Change it too much, and agreement elsewhere collapses. The cosmic microwave background would no longer match predictions. Galaxy clustering at late times would deviate. Once again, the corridor of viability is narrow. Dark matter can be tweaked, but only slightly, and slight tweaks may not be enough. Some researchers have proposed that the universe began with unusually large initial fluctuations. If the seeds of structure were stronger than we think, growth could proceed more quickly. But these initial fluctuations are tightly constrained by the cosmic microwave background. They cannot be arbitrarily large. This avenue appears closed, which leads to more radical possibilities. One of the most discussed involves early black holes. If large black holes formed very early, perhaps directly from collapsing gas clouds, they could accelerate galaxy formation by acting as gravitational anchors. Matter would fall inward more rapidly. Structure would organize around them. This idea shifts the burden from stars to black holes. But it introduces new problem. Direct collapse black holes require rare conditions. They are difficult to produce frequently, yet early massive black holes appear common. Explaining a population requires a mechanism that operates broadly. rare events do not scale. Another class of explanations considers changes to gravity itself. Perhaps gravity behaved differently in the early universe. Perhaps its strength varied subtly with energy scale or environment. Modified gravity theories have been proposed for decades, often to address other cosmological tensions. Applying them to early structure formation is tempting, but gravity is one of the most precisely tested forces in physics. Altering it risks conflict with observations across many scales. Any modification must be subtle, temporary, and carefully constrained. This again limits freedom, which brings us to a quieter but deeper idea. Perhaps the early universe was not governed by a single dominant process. Perhaps multiple effects overlapped: slightly enhanced star formation, slightly altered dark matter behavior, slightly modified feedback. Individually insufficient, together enough. This hybrid approach spreads the burden. It avoids dramatic changes, but it introduces complexity. And complexity, in theory, comes at a cost. The more parameters a model has, the less predictive it becomes. It can explain anything, and therefore explains nothing. This is the danger zone, where explanation becomes accommodation, where understanding gives way to adjustment. The early universe anomaly sits uncomfortably close to this zone, because none of the proposed explanations stand alone. Each requires assistance. Each solves part of the problem. None solve all of it, which suggests that the true explanation may lie outside the current menu of ideas. History offers a lesson here. When multiple partial explanations fail, it is often because the correct explanation has not yet been imagined. The anomaly is not asking for better tuning. It is asking for a new perspective. One possibility, still speculative but increasingly discussed, is that the early universe passed through a brief period of altered dynamics. Not a permanent change, not a new force, but a transient phase. A window during which structure formation was dramatically enhanced. Once that window closed, the universe settled into the behavior we observe today. This idea is appealing because it preserves most of modern cosmology while explaining early anomalies. But identifying such a phase is difficult. It must leave subtle signatures. It must not disrupt later evolution, and it must arise naturally from deeper physics. At present, it remains an idea without a mechanism, which brings us to the core difficulty. Every explanation so far either breaks something else or fails to explain enough. This is not a failure of creativity. It is a signal that the problem may be pointing toward physics that does not fit neatly into existing categories. The early universe may have operated under principles that we have not yet formalized, principles that govern how complexity emerges under extreme conditions. And until those principles are understood, the anomaly remains, not as an embarrassment, but as an invitation. As explanations grow more complex, a subtle shift begins to occur. The question quietly changes. It is no longer how these early structures formed. It becomes why the universe allows such formation at all. Because beneath every proposed mechanism lies an assumption that is rarely questioned, that complexity is difficult, that it must overcome resistance, that it is the exception, not the rule. But the early universe does not appear to share that assumption. Instead, it behaves as though complexity is favored. This realization unsettles more than cosmology. It challenges how we think about the nature of physical law. One of the most radical ideas now circulating does not involve new particles or forces, but a reinterpretation of emergence itself. In this view, complexity is not a fragile byproduct of cosmic evolution. It is a natural outcome once certain thresholds are crossed. Matter does not struggle to organize. It cascades into structure. Under extreme conditions, small differences amplify rapidly. Organization becomes efficient, not expensive. This idea reframes the early universe as a system poised near criticality, a state where minor perturbations trigger large-scale order. Such systems are well known in physics. Near critical points, behavior changes dramatically. Correlations extend across scales. Local interactions produce global structure. If the early universe existed near such a point, structure formation would accelerate, galaxies would appear quickly, black holes would grow rapidly, complexity would emerge without delay. This does not require new forces. It requires new context. The early universe may have been tuned by initial conditions or fundamental constraints to a regime where organization was unavoidable. But this idea carries consequences. If complexity emerges easily under the right conditions, then the rarity we assign to certain structures may be misplaced. The universe may not be reluctant to build, it may be eager. This possibility forces a reconsideration of cosmic scarcity. We often assume that large, ordered systems are rare because they require long histories. But if time is not the limiting factor, rarity must be redefined, which leads to a more unsettling implication. If the universe organizes itself efficiently, then the emergence of complex systems may be common, not exceptional. This idea is difficult to confront because it undermines a deeply held intuition that we exist at the end of a long, unlikely chain of events. But the early galaxies suggest that chains may be shorter than we thought, that the universe does not wait to explore its possibilities. This does not mean that everything exists everywhere. It means that when conditions allow, complexity follows quickly, and this realization feeds back into cosmology. Because if complexity emerges rapidly, then early cosmic history becomes more crowded, more eventful, more structured. The universe may have hosted rich environments far earlier than expected. This does not imply life. It implies potential, and potential is enough to disturb comfortable narratives. Some researchers resist this direction because it feels speculative, but speculation is not the issue. The issue is implication. Once complexity is no longer rare, the universe feels different, less empty, less indifferent, more active. This does not anthropomorphize the universe. It simply acknowledges that physical systems can self-organize efficiently under the right conditions. The early universe may have been such a system. Another unsettling explanation considers information itself. Some physicists have begun to explore whether information, rather than matter or energy, plays a deeper role in cosmic evolution. In this view, the universe evolves in ways that maximize information processing or structure. This idea is controversial, but it offers a different lens. If the universe favors states that encode more information, then the rapid emergence of complex structures is not surprising. It is expected. Early galaxies would represent early information-rich systems. This does not require intention, it requires law. But such ideas push physics toward philosophy. They blur boundaries, and blurred boundaries make scientists uncomfortable. Yet discomfort has historically accompanied progress. The early universe may be forcing such discomfort because conventional explanations keep failing. And when conventional explanations fail, unconventional ones gain traction, not because they are proven, but because they may be necessary. Another proposal suggests that cosmic evolution is path-dependent, that small differences early on determine everything that follows. In such systems, early efficiency matters enormously. If structure formation began slightly faster than expected, it would cascade. Early galaxies would form quickly. They would merge. They would seed larger structures. The universe would snowball into complexity. This idea emphasizes sensitivity rather than novelty. It suggests that the early universe did not need new physics, only favorable conditions. But even sensitivity requires explanation. Why were conditions favorable? Why did the universe sit near thresholds rather than far from them? This question does not have a comfortable answer. It points toward deeper principle. Perhaps the early universe was constrained by conditions we do not yet understand. Perhaps the space of possible universes is narrower than we think. Perhaps universes that fail to organize quickly simply do not persist. These ideas verge on speculation, but they are responses to a real problem. The early universe behaved in ways that our current intuition does not predict. And when intuition fails, deeper structure is often at work. The difficulty lies in distinguishing meaningful insight from narrative comfort. Not every explanation deserves equal weight, but the persistence of the anomaly demands openness. It demands that we consider explanations that challenge assumptions rather than reinforce them. The early galaxies are not asking for clever adjustments. They are asking why complexity appeared so easily, why the universe did not remain simple longer, why order did not wait. This question lingers beneath every proposed mechanism, and it refuses to be silenced. Because each explanation, no matter how technical, circles back to the same unsettling theme. The universe may be better at building itself than we assumed, and that possibility has consequences that extend far beyond cosmology. As these ideas accumulate, the shape of the problem begins to change. What started as a question about early galaxies becomes a question about cosmic history itself. Because once complexity is allowed to emerge rapidly, the traditional timeline begins to lose meaning. Cosmic history is often presented as a sequence of milestones: first stars, first galaxies, first heavy elements, each separated by long delays, each earned slowly through time. But the early universe does not appear to respect that pacing. Instead, it compresses milestones. Events we thought were separated by billions of years appear to cluster together near the beginning. This compression forces a re-evaluation of what early actually means. Early may not imply primitive. It may simply imply extreme. Under extreme conditions, systems behave differently. Processes that are slow under ordinary circumstances accelerate. Barriers that usually limit growth weaken or disappear. The early universe was nothing if not extreme. Temperatures were high, densities were immense, energy flowed freely. Under such conditions, the distinction between possible and impossible shifts. What we consider difficult today may have been trivial then. This reframing alters how we interpret the absence of evidence. We often assume that if something did not exist early, it is because it could not have. But absence may simply reflect erasure. The universe is not a static archive. Structures merge, the signals dilute, information fades. What remains visible after billions of years is a biased sample of what once existed. Large, robust systems survive. Small, transient ones vanish. If the early universe was more complex than we thought, much of that complexity may have been lost. Only the most durable structures remain. The early galaxies we observe may be survivors, not pioneers. They may represent the tail end of a much richer early landscape. This possibility deepens the discomfort, because it suggests that our picture of early cosmic history is incomplete, not only because of theoretical limits, but because of observational erasure. We are trying to reconstruct a turbulent past from its ruins. And ruins rarely tell the whole story. This realization complicates explanation. It means that even if we identify mechanisms capable of producing early galaxies, we may still underestimate the universe's early activity. The visible anomalies may be the tip of a much larger iceberg, which raises a difficult question. If complexity emerged rapidly and extensively, why does the universe appear relatively quiet today? Why did this activity not persist? One answer lies in expansion. As the universe expanded, densities dropped, energy thinned, conditions changed. Processes that were efficient early became sluggish. The universe settled. This is not unusual in physical systems. Rapid transitions often occur early, followed by long periods of stability. The early universe may have experienced such a transition, a burst of organization, followed by a long decay into gradualism. If so, then modern cosmology may be accurately describing the universe after it settled, but not while it was settling. This distinction matters because it suggests that our models are not wrong. They are late. They describe the aftermath, which means that early anomalies are not contradictions. They are artifacts of a regime change. This view reframes the problem. Instead of asking how the early universe violated our models, we ask why our models apply so well later, but not earlier. The answer may be that the universe crossed a threshold. Before the threshold, behavior was different. After it, behavior stabilized. Identifying that threshold becomes crucial. It may be associated with changes in expansion rate, with cooling, with symmetry breaking, with the decoupling of forces, or with processes we do not yet recognize. The difficulty is that thresholds leave subtle traces. They do not announce themselves clearly. They must be inferred from anomalies. The early galaxies may be such anomalies. They mark where our expectations break. And once expectations break, interpretation must follow. This also reshapes how we think about cosmic inevitability. If complexity emerges quickly and then stabilizes, then the universe's overall structure may be robust. It may not depend sensitively on long timelines. Instead, it may depend on crossing certain conditions. Once crossed, outcomes follow. This has philosophical implications. It suggests that the universe's large-scale organization is not precarious. It is resilient. It emerges reliably under a wide range of conditions, which makes the early universe less mysterious but more powerful. It is not struggling to organize. It is expressing what physical law permits. And physical law, under extreme conditions, may permit much more than we assume. This realization does not resolve the anomaly, but it contextualizes it. It suggests that the early galaxies are not violations, but indicators. Indicators that the universe's capacity for self-organization has been underestimated, and that under the right conditions, complexity emerges rapidly. This idea echoes through other areas of physics. In chemistry, complex molecules self-assemble under the right conditions. In biology, structure emerges spontaneously from simple rules. In condensed matter, order appears abruptly near critical points. The universe itself may behave similarly. On cosmic scales, it may self-organize once constraints loosen. The early universe may have been such a moment. This does not mean that anything was possible. It means that more was possible than we thought. And that realization forces a recalibration of our sense of scale. What we thought required patience may have required only opportunity. And opportunity was abundant at the beginning, which brings us back to the core tension. The early galaxies challenge not just models, but intuition. They force us to confront the possibility that our sense of cosmic pacing is wrong, that the universe does not move at the speed we imagine, that when conditions allow, it moves quickly. And that realization changes how we interpret everything that follows. Because once the universe demonstrates that it can organize itself rapidly, the question becomes not how rare complexity is, but how often it emerges when given the chance. This question extends beyond galaxies. It touches the formation of stars, of planets, of environments capable of sustained processes, and it quietly undermines narratives built on rarity and delay. The early universe may have been far more active than we have allowed ourselves to believe, and the galaxies that should not exist may be the clearest evidence of that activity. They stand as reminders that the universe's history is not a gentle slope. It is a steep climb, one that began almost immediately. At this stage, something important becomes clear. Every explanation on the table succeeds only by narrowing its focus. Each addresses one dimension of the problem while leaving others unresolved. Faster star formation explains mass, but not stability. Altered dark matter behavior explains collapse, but not consistency. Early black holes explain structure, but not frequency. Critical transitions explain speed, but not origin. Each idea illuminates part of the landscape. None illuminate all of it. This is not because the ideas are careless. It is because the problem is not localized. It spans multiple layers of cosmic evolution simultaneously. Galaxies form too early. Black holes grow too fast. Chemistry matures too quickly. Structure stabilizes prematurely. These are not separate anomalies. They are manifestations of the same underlying tension. Time behaves differently than expected, and time in cosmology is the ultimate constraint. When explanations begin to fail collectively, a deeper diagnosis becomes unavoidable. The issue is not which mechanism dominated. It is that the early universe appears to have operated in a regime where constraints we consider fundamental were relaxed. Not eliminated, relaxed. Processes that are slow today may have been fast. Processes that are inefficient today may have been efficient. Processes that compete today may have aligned. This alignment is difficult to capture in isolated models. It suggests coordination rather than coincidence. And coordination in physics usually points to deeper structure, something organizing the organizing processes. This is where explanation begins to approach its limit, because once you posit deeper structure, you must ask where it comes from, and that question cannot be answered by adjusting parameters. It requires new principles, not necessarily new forces or particles, but new ways of thinking about how physical law expresses itself under extreme conditions. The early universe may not have been governed by a different set of laws, but it may have explored a different region of the same laws, regions that are inaccessible now, regions where behavior is unfamiliar. Our current physics is shaped by what we can observe and test. The early universe lies beyond direct experiment. We infer it indirectly, and indirect inference has limits. The galaxies that should not exist push us up against those limits. They mark where inference begins to strain, and strain reveals boundaries. At these boundaries, explanation becomes less about certainty and more about plausibility. Multiple stories can fit the same facts. Which story we choose depends on deeper commitments. Do we believe the universe favors gradualism? Or do we accept that it may reorganize itself abruptly? Do we believe complexity is fragile? Or do we accept that it may emerge robustly under the right conditions? These are not empirical questions alone. They are interpretive ones. They guide how we build models, and they influence what we consider reasonable. The early universe forces us to revisit these commitments because the data does not align cleanly with our preferences. It resists being folded into familiar narratives, and that resistance is informative. It tells us where our intuition fails. In physics, intuition is shaped by experience. Our experience is limited to a calm, late-time universe. We extrapolate backward and assume continuity, but continuity may not hold. The early universe may have been qualitatively different, and if so, then the failure of our explanations is not surprising. We are trying to understand a foreign regime using domestic tools. This does not mean explanation is impossible. It means it will not be simple. It will likely require integrating multiple ideas into a coherent picture, a picture where efficiency, thresholds, and rapid transitions are central rather than peripheral. But even such a picture may not fully satisfy, because there is a deeper discomfort beneath all of this. So, the early universe appears to challenge not just our models, but our sense of inevitability. We assumed the universe had to work hard to build structure. The evidence suggests it did not. We assumed complexity was delayed. The evidence suggests it arrived early. We assumed time was the bottleneck. The evidence suggests conditions mattered more. These shifts are subtle, but profound. They alter how we think about cosmic evolution. They suggest that the universe is not a reluctant builder. It is an efficient one, and efficiency changes how we interpret rarity. If complexity emerges readily under certain conditions, then the early universe may have been crowded with events we can no longer see. The galaxies that remain may be survivors of a far richer past. This realization does not provide closure. It deepens the mystery, because if the early universe was capable of so much, then our current picture is incomplete not just in detail, but in scope. We are missing chapters, and missing chapters mean missing context, which brings Section 3 to its conclusion. We have explored the possible explanations. We have seen how each one helps and how each one fails. We have pushed against the limits of current thinking. And in doing so, we have arrived at a difficult truth. The problem is not that we lack ideas. It is that none of the ideas fully explain what we see. The early universe continues to resist capture, and that resistance is not a dead end. It is a signal that something deeper is at work, something that connects efficiency, time, and structure in ways we do not yet fully understand, which sets the stage for the final question. If our explanations are incomplete, what does that imply for how we understand the universe itself? That question will guide the final section. Once it becomes clear that existing explanations fall short, the problem changes character. It is no longer about fixing models. It becomes about direction. Because when a scientific framework encounters a persistent anomaly, the most important question is not how to remove it, but what it is pointing toward. Anomalies are rarely random. They cluster where understanding is weakest. And in cosmology, that place has always been the beginning. The early universe is not just distant in time, it is distant in accessibility. We cannot recreate it. We cannot experiment on it directly. We infer its behavior from faint signals carried across billions of years. This makes progress slow and cautious. But it also means that when multiple independent observations converge on the same tension, that tension deserves attention. The galaxies that should not exist have done exactly that. They have forced cosmology to confront the possibility that the early universe was governed by principles that are not fully captured by our current descriptions. This does not mean abandoning physics. It means extending it. In the past, such extensions have not come from speculation alone. They have come from necessity. Newtonian gravity worked until it didn't. Classical physics explained heat until it didn't. The universe appeared static until it didn't. Each time, observation forced theory to grow. The early universe may be forcing another such growth, but growth does not always look dramatic. Sometimes it begins quietly, with a shift in emphasis. Already, cosmology is changing how it frames questions. Instead of asking how long processes take, researchers are increasingly asking under what conditions they occur. Time may not be the fundamental variable we assumed. Conditions may matter more. If certain thresholds are crossed, processes accelerate. If not, they stall. This conditional view of cosmic evolution aligns with what we see in other complex systems. In many physical systems, behavior is not linear. Nothing happens until suddenly everything does. The early universe may have followed this pattern. If so, then our future models will need to focus less on smooth timelines and more on regime changes, on identifying when the universe shifted from one mode of behavior to another. This requires new kinds of data, more precise observations of early galaxies, better measurements of their masses and compositions, clearer timelines of star formation and black hole growth. Upcoming observatories are designed with this in mind. They will not simply catalog objects. They will probe structure. They will test whether early galaxies are common or exceptional, whether rapid formation was universal or localized, whether early complexity is the rule or the outlier. These observations will not immediately resolve the anomaly, but they will constrain it. They will tell us whether we are dealing with a narrow problem or a broad one. And that distinction matters. If only a few galaxies defy expectation, explanations may remain specialized. If many do, the framework must adapt. There is also a shift happening at the theoretical level. Researchers are increasingly willing to consider that early universe physics may involve emergent behavior. That complexity arises not from detailed tuning, but from collective effects. In such systems, global behavior cannot be predicted by examining parts in isolation. This challenges reductionism. It suggests that understanding the early universe may require thinking in terms of systems rather than components. This is a significant shift. Physics has traditionally excelled by breaking problems into smaller pieces, but some phenomena resist this approach. They require holistic thinking. The early universe may be one of them. If structure formation was a collective phenomenon driven by interactions across scales, then simple, linear models will fail. This does not make the problem unsolvable. It makes it different, and difference requires adaptation. Already, cosmology is borrowing ideas from other fields, from statistical mechanics, from complexity science, from non-linear dynamics. These fields study systems where small changes can produce large effects, where order emerges spontaneously, where history matters. Such ideas may be essential for understanding why the universe organized itself so quickly. But even as methods evolve, one thing remains constant. The anomaly does not disappear. It continues to shape how questions are asked. And this is perhaps its most important role. It forces humility. It reminds us that our understanding of the universe is provisional, that success in one regime does not guarantee success in all, that the early universe may still hold surprises capable of reshaping our worldview. This realization has implications beyond cosmology, because the story we tell about the universe influences how we think about our place within it. We often imagine ourselves at the end of a long, improbable process, a fragile outcome of billions of years of slow evolution. But if complexity emerges quickly when conditions allow, then the universe may be more generative than we assumed. This does not diminish significance, it reframes it. It suggests that the universe is not hostile to structure. It may be conducive to it, and that possibility changes how we think about cosmic history, not as a reluctant march toward order, but as an exploration of what physical law permits. The early universe may have been the most expressive phase of that exploration, and the galaxies that should not exist may be echoes of that expression. This is where the future of cosmology lies. Not in eliminating anomalies, but in understanding what they reveal. The universe is telling us something about itself, not loudly, not dramatically, but persistently, and listening requires patience, because understanding beginnings has always been the hardest task in science. When cosmology confronts its own limits, the consequences extend beyond equations. They reach into interpretation, into meaning, into how we understand the universe as a whole. The early universe anomaly does not merely challenge technical models, it challenges a narrative that has quietly shaped modern thinking. The idea that complexity is late, fragile, and unlikely. This narrative has been comforting. It suggests that order must be earned, that time is the great gatekeeper, that the universe begins simple and reluctantly allows complexity to emerge. But the early galaxies suggest a different story. They suggest that complexity is not an afterthought. It may be a natural expression of physical law. This does not mean that the universe is design. It means that the universe may be structured in such a way that organization is not difficult under the right conditions. This distinction matters because we often mistake difficulty for meaning. We assume that because something took a long time to happen, it must be rare or special. But rarity is not the same as significance, and time is not the same as improbability. If the universe is capable of rapid organization, then complexity may arise whenever conditions permit, not eventually, immediately. This reframing shifts how we think about cosmic history. The early universe stops being a blank waiting room. It becomes an active phase, a period where physical law explores its full expressive range. In this view, the universe is not passively cooling into order. It is actively discovering what it can become. This perspective does not add intention. It adds agency to law itself. Physical law is not static instruction. It is dynamic possibility. Under different conditions, it yields different outcomes. The early universe was such a condition, and the galaxies that should not exist may be proof that the universe did not hesitate to explore that possibility space. This realization is unsettling because it dissolves a comforting distance. We often place complexity far from the beginning to preserve a sense of narrative buildup. But the universe may not follow narratives. It may follow thresholds. Once crossed, outcomes follow rapidly. And if thresholds matter more than duration, then the universe's story becomes less linear, more conditional, more contingent. This has implications for how we think about inevitability. We like to believe that the universe had to unfold the way it did, that the long delay before complexity was necessary, that the outcome required patience. But if complexity emerges readily under certain conditions, inevitability becomes less clear. The universe may have had many possible histories, some slow, some fast, some rich, some sparse. The early universe we observe may be just one realization among many, and that realization may not have been particularly constrained. This idea challenges a subtle assumption that our universe is finely balanced. Instead, it may be broadly permisception. The early universe may not have needed tuning to produce structure. It may have needed only opportunity, and opportunity was abundant. This perspective reshapes how we think about cosmic luck. We often frame existence as improbable because we imagine long chains of unlikely events. But if chains are short, improbability diminishes. This does not trivialize existence. It changes how we measure its contingency. It suggests that complexity is not balanced on a knife's edge. It may be robust, resilient, eager to emerge. This is not a comforting thought. It removes the idea that order is precarious. It implies that the universe builds when it can, and this realization forces a reconsideration of scale. We tend to imagine cosmic history as slow because our intuition is calibrated to human time. But the universe is not obligated to move at our pace. What feels rapid to us may be glacial in cosmic terms, and what feels slow to us may be explosive at the beginning. The early universe may have experienced a kind of acceleration of meaning, a period when everything that could happen happened quickly, then stabilized, then coasted. If so, then much of what we observe today is the aftermath of that initial burst, and the galaxies that should not exist are remnants of that moment. This does not mean we understand that moment. It means we recognize its importance, and recognition is the first step toward understanding. The deeper implication is this: the universe may not be a system that gradually builds toward complexity. It may be a system that expresses complexity whenever constraints loosen. This shifts the focus from time to permission. When conditions allow, structure appears. When they do not, it fades. This dynamic view of the universe aligns with many areas of modern science. In non-equilibrium systems, order emerges far from equilibrium. In biological systems, complexity appears rapidly when resources align. In social systems, structure forms suddenly when thresholds are crossed. The universe may not be an exception. It may be the largest example. This does not reduce mystery, it deepens it. Because if complexity emerges naturally, then understanding the universe requires understanding the conditions that enable it, not just the passage of time. The early universe may have been a perfect storm of such conditions: high energy, high density, rapid expansion. Together, they may have created a regime where organization was unavoidable. This is not a final answer. It is a reframing, and reframing is powerful because it changes what we look for. Instead of asking why complexity appeared early, we ask why it would not have. Instead of assuming delay, we assume readiness. Instead of viewing anomalies as violations, we view them as expressions. The early galaxies become less disturbing under this lens. They become informative. They tell us what the universe does when it is unconstrained. And that may be the most important lesson of all. Even if the details of this anomaly are never fully resolved, its significance does not disappear, because some questions matter not for their answers, but for how they change the way we think. The early universe may always remain partially opaque. Its conditions may never be reproduced. Its full dynamics may never be observed directly. But opacity does not mean irrelevance. It means limitation, and limitation, when acknowledged, reshapes understanding. The galaxies that should not exist force us to confront a simple but uncomfortable truth. We do not fully understand beginnings, and that matters, because beginnings set tone. They shape expectations. They influence how everything that follows is interpreted. For a long time, cosmology has relied on a story of restraint, a universe that begins simple, that resists organization, that allows complexity only after long delays. This story made sense. It aligned with intuition. It aligned with gradualist thinking. But the early galaxies quietly undermine it. They suggest that the universe did not resist organization. It embraced it. And that shift from resistance to readiness changes how we relate to cosmic history. We stop viewing complexity as a fragile accident. We begin viewing it as an expression of what physical law permits under extreme conditions. This does not answer every question, but it reframes the most important one. Instead of asking why the universe produced structure, we ask why it would not. This is a subtle inversion, but a powerful one. It moves mystery from outcome to condition, and condition is something science can eventually explore. This reframing also affects how we think about knowledge itself. We often assume that understanding progresses linearly, that we accumulate facts until clarity emerges. But history shows otherwise. Understanding advances through tension, through moments when reality refuses to fit, through anomalies that persist. The early universe anomaly is such a moment. It does not overthrow cosmology. It humbles it, and humility is productive. It keeps inquiry open. It prevents premature closure. It reminds us that even our most successful theories are provisional. This humility is especially important in cosmology, where direct experimentation is impossible. We rely on inference. Inference requires caution, and caution requires accepting that some answers may remain incomplete. But incompleteness is not failure. It is an honest boundary, and boundaries are where curiosity thrives. The galaxies that should not exist mark one such boundary. They sit at the edge of what we can explain. They remind us that the universe is larger than our stories, and that reminder matters regardless of resolution, because it guards against complacency. It keeps cosmology from becoming mythology. There is also a deeper, quieter implication, one that has nothing to do with equations. When we imagine the universe as reluctant to organize, we place ourselves at the end of an unlikely journey. When we imagine it as capable of rapid organization, we place ourselves inside an active process. The difference is subtle, but it changes perspective. The universe becomes less like a machine ticking reluctantly forward, and more like a system exploring its own possibilities. This does not diminish human significance. It contextualizes it. It suggests that complexity is not a violation of cosmic order. It is a manifestation of it. And that realization alters how we think about belonging. We are not latecomers to a quiet universe. We may be participants in a universe that has been expressive from the beginning. This does not imply purpose. It implies continuity. The same principles that allowed early galaxies to form quickly allow complexity to persist now. The universe did not change its mind. It changed its conditions, and conditions matter. This perspective also reframes uncertainty. Instead of fearing unknowns, we recognize them as features of scale. The universe is vast. Our access to it is limited. Some mysteries will remain unresolved, not because they are unimportant, but because they lie beyond our reach. The early universe may be one of them, but even unreachable mysteries shape understanding. They define where confidence ends and where wonder begins. The galaxies that should not exist occupy that space. They are not paradoxes demanding resolution at any cost. They are reminders that the universe is not obligated to be fully legible, and that is not a weakness of science. It is a strength. Science progresses by knowing what it does not yet know, and the early universe is now firmly in that category. This realization does not end inquiry. It refines it. It shifts focus from certainty to exploration, from answers to conditions, from closure to openness. And that shift may be the most valuable outcome of all, because it keeps cosmology alive, dynamic, responsive. The universe is still teaching us how to ask better questions, and the galaxies that should not exist are among its most patient instructors. There is a temptation, when faced with unresolved questions, to rush towards certainty, to force an answer, to believe that if we cannot explain something fully, it must be an error, either in observation or interpretation. But the universe does not reward impatience. It reveals itself slowly, indirectly, often reluctantly. The early galaxies ask us to slow down, not because the problem is small, but because it is deep. They exist at a boundary between what we can explain and what we can only infer. And boundaries are not meant to be crossed hastily. They are meant to be studied. For centuries, cosmology has been driven by a powerful idea that the universe unfolds according to a comprehensible sequence, that with enough data, enough precision, enough refinement, the story becomes clear. And in many ways, this has been true. We understand expansion. We understand background radiation. We understand large-scale structure. But understanding does not arrive all at once. It arrives unevenly, and the early universe remains one of its most uneven territories. The galaxies that should not exist are not mistakes in the data. They are not glitches. They are not gaps to be patched. They are signals that the universe still contains regions of behavior we do not yet fully understand. And that realization is not disappointing. It is grounding. It reminds us that cosmology is not finished, that the universe is not a solved puzzle, that even its opening chapter resists simplification. This resistance matters because it protects us from mistaking models for reality. Models are tools. Stories are scaffolding. Reality is something else entirely. The early universe does not conform neatly to the stories we prefer. It challenges them quietly, persistently, without spectacle. And that is how the most important challenges usually arrive, not as revolutions, but as inconsistencies that refuse to disappear. The galaxies that should not exist do not announce a new theory. They announce a limit, a point where explanation pauses. And pause is not stagnation. Pause is reflection. It gives space for better questions to form. Perhaps the most important lesson here is not about galaxies at all. It is about humility, about recognizing that our understanding of the universe is not a finished map, but a working draft, that some regions are sketched lightly, that some connections remain unclear, and that this is not a flaw, but a feature of honest inquiry. The early universe reminds us that reality is larger than our expectations, that it may operate under conditions that no longer exist, that some of its behavior may never be fully reconstructed. But even partial understanding has value because it reshapes perspective. It teaches us where certainty ends and curiosity begins. And that boundary is where science is most alive. In the end, the galaxies that should not exist do not diminish the universe. They deepen it. They remind us that complexity may not be a rare exception, but a natural outcome. That structure may not need permission from time, that under the right conditions, the universe builds quickly and moves on. And perhaps that is the quiet truth hidden in this anomaly. Not that the universe broke its rules, but that the rules were never as narrow as we assumed. The early universe did not wait. It acted, and what it left behind, faint, distant, unresolved, continues to challenge us, not with answers, but with a reminder that even now, after centuries of observation, the universe still contains places where our understanding ends, and that those places matter because they tell us where to look next.